Hi everyone, I'm Jeremiah Blanchard, and in this video we're going to talk about rule-based systems. When we speak of computers, we often use words like reason and logic. But in reality, at the core, a computer is nothing more than a very expensive, very fast, very efficient calculator. The core of a computer is an ALU, an arithmetic logic unit, which adds, subtracts, multiplies, divides, shifts, and jumps. So as a result, if we want computers to engage in logical deduction and logical induction, we have to build specific constructs for that purpose. One way to build such constructs is what we call a rule-based system, which uses logical deduction to derive new knowledge from existing data. In a rule-based system, we store all information that an agent has about its universe in a construct known as a knowledge base. And the knowledge base has two particular types of data. What we call known facts, or just facts for short, are direct, unconditional statements. Rules, which are used for deriving new information, are conditional. If one thing is true, then another thing is true. These rules are typically AND-based. That is to say, we can have two conditions for one result that are both required. But this is not necessary for OR statements, because if one thing or another must be true, we can split that up into two separate rules that both trigger the same result. Let's consider an example. If the player is present and the player has a gun, then the player is a threat. This example could be constructed with a single rule. On the other hand, if we have an OR-based construct, we can split it up into multiple variants. If the player has a gun or the player has a knife, then the player is a threat. This example can be split into two separate rules. If the player has a knife, then the player has a threat, followed by, if the player has a gun, then the player is a threat. This will make the process of determining outcomes more manageable. We're going to take a look at three different types of rule-based systems. Propositional logic, which is based entirely on static identifiers. First-order logic, which introduces some variables into the mix. And fuzzy logic, where we dispense with the idea of true and false as the only possibilities and have a sliding scale of truth between 0 and 1. There are two main approaches used in rule-based systems. The first, forward chaining, is fairly straightforward. Forward chaining is probably the most obvious. We take one or more facts, we combine them with a rule, and that allows us to draw a conclusion. If the facts are true and the rule is correct, then the conclusion is inescapable. It's a guarantee, it's a promise. We know it will happen for sure. Backward chaining is a little less straightforward. You might think of this as the detective method. We start from some conclusion, we trace it back to rules that might have triggered it, and that allows us to trace back to facts that may have triggered it. The complication of backward chaining is that there is more than one way to accomplish the same goal in many cases. For example, if my goal is to escape, I might hide or I might run away, and maybe both of these would accomplish my goal. For this reason, backward chaining is very good at finding out how to accomplish some goal, but it is more difficult to find out the cause of an event that has already occurred. In propositional logic, we'll combine statements based on constant identifiers, also known as propositions, with rules of the same type to derive new information. The benefit of using such a simple system is that it is very straightforward to put together, and it's very fast. In fact, you've probably already used propositional logic in some form or another, without even realizing that's what it was. If you've ever used a pound-define statement, you've made use of propositional logic. Among the drawbacks of such a system is that it is not particularly flexible. Because these are constant identifiers, because these propositions have no variables, it is very hard to take the same construct and apply it to different situations. Instead, every possible variant of a rule must be explicitly entered if it is to be triggered by the system. As an example, if our rules were if sunny, then good weather, and if rainy, then bad weather, and we added the fact sunny to the rule base, the conclusion we should be able to draw from that statement is good weather. One example of how propositional logic is used in games is in agent banter. We can have players whose dialogue is triggered by certain conditions being met. In this example, if a snake is present, then the agent will say, "I hate snakes." If a snake is present and that snake is an asp, then the character will say, "Asps, very dangerous. You go first." If a snake is present and the level is a plane, then the character will say, "I have had it with these monkey-fighting snakes on this Monday through Friday plane." If we add the facts, snake present and snake asp, then the result, the conclusion, will be that the agent will say, "Asps, very dangerous, you go first." If we want to get beyond the limitations of propositional logic, we can instead approach a problem using first-order logic, also known as predicate logic. In first-order logic, statements are made up of two parts, a predicate, which is fixed, and an identifier, which can be a variable. By introducing variables into the mix, we get a lot more flexibility, and we also get implicit, or variable-based, rules. The drawback of this approach is that we now require a formal system to put this logic together. It's no longer enough to establish simple identifiers using pound defines or other simple systems within a language. Instead, these systems must be explicitly built and optimized, and that means that they're going to use more resources. In fact, there are entire languages built on this concept. Our next example utilizes rules that also have variables embedded in them. In this example, within our rule base, we will represent here capital X is the variable name. Our rules are if animal X and barks X, then dog X. And if mammal X, then animal X. We're then going to add the facts mammal Fido and barks Fido. When we add mammal Fido, that will allow us to draw the conclusion animal Fido. Later, when we add barks Fido, that allows us to draw the conclusion dog Fido. In games, fuzzy logic extends the ideas of first-order logic one step further by removing the requirement that values must be either true or false, and instead allows them to be true, false, or any value in between. We have a sliding scale, a truth value between 0 and 1. This introduces even greater flexibility into the system. Whereas before we had implicit rules, now we have implicit truth degrees. Because small changes in the input can result in very large changes in the results, this can give the impression of randomness or emergent behavior. But make no mistake, fuzzy logic is not random. It is 100% completely deterministic. However, from a user's perspective, because small variations in data can result in bigger variations in behavior, it may appear to be random, or at least not predictable. The drawbacks are, it's even slower and uses more resources. This is less pronounced today than it was in the past, but it's still a consideration. Let's take a look at a couple of examples. Let's say we were trying to determine the truth of whether or not someone is short, medium, or tall. If someone is above 6'6", we might say it is 100% true that they are tall, it's 0% true that they're medium, and it's 0% true that they're short. However, as we slide down in height, the truth value of tall begins to go down while the truth value of medium begins to go up. Perhaps at 6'3", it might be 50% true that that person is tall and 50% true that that person is medium, but still 0% true that that person is short. When we reach 6'6", it is now 0% true that that person is tall, 100% true that that person is medium, and 0% true that that person is short. Continuing down, when we hit 5'9", perhaps that is 50% each, short and medium, and 0% tall. And as we proceed, the values continue to change. Once we reach 5'6", and for any height below 5'6", we may say that it's 100% true that a person is short, and 0% true that they are medium or tall. Let's consider a game-based example. Here, we will have 3 truth values, health, shields, and ammo. For our agent Bob, we'll say that it's 70% true that he's healthy. In other words, he has 70% of his max health. He has 10% of his shields, and he has 50% of his max ammo. For simplicity, we'll assume that there's only one type of ammo. Our rules will be, if an agent is healthy and has shields and has ammo, that agent should attack. If an agent is healthy and does not have shields but does have ammo, that agent should defend. And if an agent is not healthy and does not have shields, or if an agent is not healthy and does not have ammo, that character should try to escape. Because our last rule has an or, we will split it up into 2 separate rules. If an agent is not healthy and does not have shields, that agent should escape. And separately, if an agent does not have health and an agent does not have ammo, that agent should try to escape. In this particular example, we will use the minimum to replace AND functions and maximum to replace OR functions. There are other variations on fuzzy logic systems, but this is probably the most common. If we need to calculate a not value, we're going to use 1 minus the value. To calculate Bob's attack tendency, we're going to take the minimum of his health, shields, and ammo, because this is an AND statement. The minimum of 0.7, 0.1, and 0.5 is 0.1. So Bob's attack tendency is 0.1. Bob's defend tendency is going to be a little trickier. First, we have to calculate the not value for shields. If shields is 0.1, 1 minus 0.1 is 0.9. If we then take the minimum of 0.7, 0.9, and 0.5, that value is 0.5. So Bob's defend tendency will be 0.5. Our next two rules in the system, generated by splitting the OR, will calculate the not health value first. If his health is 0.7, not health is 0.3. We've already calculated not shields to be 0.9. The minimum of 0.3 and 0.9 is 0.3. So the first calculation for Bob's escape tendency is 0.3, but we have another value to calculate. We already know that not health is 0.3, so we need to calculate not ammo. If his ammo is 0.5, 1 minus 0.5 is 0.5, so not ammo is also 0.5. The minimum between 0.3 and 0.5 is 0.3. So we have our second calculation for Bob's escape tendency, which is 0.3. At this point, if we have multiple values for the same tendency, we will take the maximum of those values to represent the OR. In this case, there's no difference, but if it were 0.5 and 0.3, we would choose the 0.5. Looking at these results, Bob's highest tendency would be to defend. However, there are many ways to interpret this data, which we will look at moving forward.